Good evening, everyone. This is Mr. Stelzer. Well, it's evening where I am, or when I am. I don't know when you're watching this. Anyway, regardless, we're going to do the AP Chemistry Unit 6 exam review, and this video we will be doing the multiple choice. So 14 multiple choice questions. You guys will get 21 minutes to do it. It'll probably take me longer than 21 minutes because I'm going to be explaining everything. But without further ado, let's go ahead and get into it. I'll put myself a little more up. All right. Get comfy. All right. A sample of whatever that is exposed to a constant source of heat for a period of time. The graph above shows the change in the temperature. We know what this graph is. We've seen one of these graphs before. This is just a heat versus temperature curve. Which of the following best describes what occurs at the particle level that makes segment D longer than segment B? So why is this section longer than this section? The reason why is because this section we're going from liquid to gas, which is breaking all of the IMFs. In this section, we are going from solid to liquid, which breaks some of the IMFs. So we are completely severing the IMFs when we're vaporizing. So the energy with vaporization is typically a lot higher. So whichever one says that. Specific heat capacity, it's none of those two. We don't even use specific heat capacities for phase changes. This one's just wrong. The enthalpy of fusion is not greater than the enthalpy of vaporization. The enthalpy of vaporization is greater than the enthalpy of fusion because separating molecules completely from the liquid to form a gas requires more energy than separating molecules from their bound crystalline state as a solid. A lot of complicated terminology in there, but yeah, that's what it is. We're separating those molecules completely. That's the key, separating molecules completely. A mixture of NO2 gas and N2O4 gas is placed in a glass tube and allowed to reach equilibrium at 70 degrees Celsius as represented above. Which of the following statements about delta H for the reaction is correct? Okay, right away, there's actually a lot of things in this problem that you don't know yet. We haven't done some of these units yet. We haven't done this. You don't know what that means. You don't know what that means. This whole thing, that's the equilibrium constant. I actually added that. But we don't need that. As a matter of fact, we don't even need any of this at all. Let's just look at the answers. We have enthalpy is exothermic. Remember, delta H greater than 0 is exo. Delta H, or I said greater, but I wrote less. Delta H less than 0 is exo. Delta H greater than 0 is endo. So the reaction is exothermic because energy is released when the N-N bonds break. Nope, because that and that energy is released don't match. We don't release energy when we break bonds. We release energy when we form bonds. It takes energy to break bonds. Delta H is exothermic because energy is required to break N-N bonds. Also no. That and that don't match. If energy is required, it should be endo. Delta H is greater than 0, so it's endothermic because energy is released. Nope, that and that don't match. And then enthalpy is endothermic because energy is required to break N-N bonds. That's our answer. That's the only one that actually matches up with what it's saying. And that is true for this question. If we look closely at these molecules, the only difference is we have this N2O4, probably is going to look something like this. I don't know everything, but it's going to look something like that. And all we're doing is we're just severing, breaking that bond in the middle. So it should be endothermic, so D. But we didn't even need to know that. It's just 3 of these didn't make sense. The oxidation of carbon monoxide can be represented by the chemical equation there. The table above provides the average bond enthalpies for different bond types. Based on the information in the table, which of the following mathematical expressions is correct for the estimated enthalpy change for the reaction? All right, we're given bond energies. So what are we going to do? We're going to do the bond energy equation. The enthalpy of the reaction is equal to the sum of the bonds broken broken, which is all of the endothermic ones, minus the sum of the bonds formed, which is the endothermic. So in other words, these are the reactants, these are the products. So let's look at the reactants for its carbon monoxide. We do have to make some Lewis structures here. Carbon monoxide looks like this. All right, I don't have a periodic table nearby. Nope. All right, carbon has 4. Oxygen has 6. It's going to be triple bond, so 4 plus 6 is 10. It's going to look like that. Oxygen gas has a double bond. And carbon dioxide also has double bonds. So it's going to be 2 times whatever this one is, which is 1072, plus 100 double bond, which is this one. Oh, no. This one, 489, minus 2 carbon dioxides, and each carbon dioxide has 2 CO double bonds, so it's going to be 4 of the CO double bonds, 799. Just to say that last part, because I feel like that's where you'll make a mistake on this question. Carbon dioxide, 1 carbon dioxide has 2 carbon-oxygen double bonds. But we have 2 carbon dioxides in the formula, so that's 4 in total. So the answer is going to be B, it looks like. I think that matches up there. All right, in the spring, the blossoms on cherry trees can be damaged when temperatures fall below -2 degrees Celsius. When the forecast calls for air temperatures to be below -5 degrees Celsius for a few hours one night, a farmer sprays his blossoming cherry trees with water, claiming that the blossoms will be protected by the water as it freezes. Which of the following is a correct scientific justification for spraying water on the blossoms to protect them from temperatures below -2 degrees Celsius? Water on the blossoms will not freeze unless the air temperature falls significantly below. Water is a good thermal conductor. Freezing of water is endothermic. Freezing of water is exothermic. Okay, so what's happening here is we have a cherry tree. I can pretend this is a cherry tree and not what looks like an apple tree. We spray water on it. So now all the cherries are a little wet. Then as the water freezes, somehow that protects the cherry trees from dying. Why is that? Because water freezing is an exothermic process. When water freezes, it has to release energy because solid is at a lower energy level than liquid. Those liquid particles are at a higher energy, so they have to release their energy in order to go to solid. And that's just enough to keep the cherry trees from, or keep those blossoms. We don't want to kill those blossoms of the cherry trees from dying. So water freezing is an exothermic process. Similarly, you can also just put a towel over your tree and put a little light underneath it. That's what me and my dad always did when it would dip below freezing here in Florida with our cherry tree out front. Okay. The equation above represents the decomposition of XY2. The diagram below shows 2 reaction profiles. Which of the following best describes the flow of heat when 1 mole of XY2 decomposes? Okay, so we're not really worried about what's happening here. We're worried about this one. So the decomposition, because that's what this graph is showing, is ending up at a higher energy level, which means this is endothermic. So, and the total energy level is 50 kilojoules per mole. So what's happening is 50 kilojoules per mole is getting absorbed from the surroundings. So that is B. 50 kilojoules of heat is transferred from the surroundings. For an experiment, 50 grams of water is added to a coffee cup calorimeter as shown in the diagram. The initial temperature is 22 and it absorbs 300 joules of heat from an object that was carefully placed inside the calorimeter. Assuming no heat is transferred to the surroundings, which of the following is the approximate temperature of water after thermal equilibrium was reached? Assume the specific heat of H2O is 4.2 joules per grams times Kelvin. All right, whenever we see, oh, this is a little nice diagram. I like that. Not that we need that at all. Whenever we see calorimetry, we should be thinking Q equals MC delta T. All right, the Q is 300 joules. The mass is 50 grams. We're going to use 4.2 for C. And I just like to solve for delta T. Some people like to just put in the T final minus T initial. I don't like to do that. I just like to solve for it. So let's solve for delta T. We get 300 divided by 50 times 4.2. Delta T is equal to 1.43 degrees Celsius. So the water absorbed 300 joules, which means the temperature is going to go up by 1.43 degrees Celsius. So 22 plus 1.43 is 22 plus 1.43 is 23.43, which matches D. So D is our answer. A piece of iron is placed into water at 75 degrees Celsius in an insulated container. A student predicts that when thermal equilibrium is reached, the iron atoms, being more massive than the water molecules, will have a higher average kinetic energy than the water molecules. Which of the following best explains why the student's prediction is incorrect? When thermal equilibrium is reached, that is when the temperatures equal each other. And temperature is a measurement of average kinetic energy. So if temperature is equal, then average kinetic energy will be equal. So it has nothing to do about the size of the particles. It has everything to do with the kinetic energy. So at thermal equilibrium, average kinetic energy cannot be greater than that of H2O molecules. The average kinetic energy must be the same according to the law of the definition of thermal equilibrium. Messed up that underline, but that is our answer there. The answer there is D. All right, for questions 8 and 9, we're going to use the following information. We're given all these tables with all these reactions. Which of the values of delta H for the process in the tables are less than 0 indicates an exothermic process. So we're predicting which of these are going to be exothermic. And to do this, this is going to be takes to break and free to form. If we are breaking any sort of bond or IMF, that means it's going to be endothermic because we need energy. We need to put in energy to break that bond. If any sort of bond or IMF is forming, then that's going to release energy. So we go from solid to gas. That is breaking. We have to break apart the solid in order to get gas molecules. We're breaking IMFs. That is going to be endo. Endo. For the second one, we are breaking something. We're breaking away an electron from potassium. That is also endothermic. That's actually would be this energy would be an ionization energy because that's the definition of ionization energy. For 3, we are taking a Cl2 and we're breaking them into 2 Cls. That is also breaking a bond, so that's also endothermic. For C, now we are forming a bond or an attractive force. We're putting together an electron and chlorine to make a chloride ion. This is exo. And for the last one, we are also bringing something together. We're bringing a potassium ion and a chloride ion to make potassium chloride. This is also exo. So the two that are exo are Y and Z, so Y and Z only. Which of the following expressions is equivalent to the delta H for the reaction represented above? All right, we have this reaction. What's the delta H of that reaction? This is a pseudo Hess's law, or is it a pseudo Hess's law or full on Hess's law problem? Oh, this is a full on Hess's law problem. This reaction is not given. But we can use some of these reactions to make this reaction. We don't have to use all of these reactions. We're not going to use any of the ones with potassium in it. Let's just look at these two. How can we rearrange those two reactions to make this one? Well, if we take X, which is, let me go move down a little bit, which is Cl2 yields 2Cl, and we flip, or we double, we're going to double Y to make 2Cl plus 2E minus yields 2Cl minus. Add those two together, and the Cl's cancel out, and we get Cl2 plus 2E minus yields 2Cl. This one's enthalpy is X. This one's enthalpy is 2Y, since we had to double that reaction. So the total enthalpy of this reaction is X plus 2Y. So that comes from Hess's law, which is C. 2 more pages. The reaction between carbon and water is represented by the balanced chemical equation above. Based on the enthalpy change of the reaction and the standard heats of formation, what is the approximate delta HF for carbon monoxide? So let's just set up our equation. We're given enthalpy of formation. Let's go to our enthalpy of formation equation on the equation sheet. I wish I had my equation sheet, but I don't. Luckily, I'm like a super genius when it comes to chemistry, and I just remember these things. The enthalpy of reaction is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. So enthalpy of formation does products minus reactants, not reactants minus products like bond energy does. So H2 does not have an enthalpy of formation because that is its natural state. Carbon monoxide is what we're solving for. So the enthalpy of the reaction is the enthalpy of formation of carbon monoxide. I'm just going to call that X. Oh, and we're given the enthalpy of the reaction, 131 kilojoules per mole. 131 equals X minus carbon also does not have an enthalpy of formation because that is its natural state. And we're looking for water. Water is negative 242. So we have negative 242. If you did not remember that enthalpy formation of compounds in their standard state, in their natural state, is 0, this question was nice enough to give you that. The question doesn't have to give you that. You should know that. All right, so 131 equals X minus a negative is positive 242. So 131 minus 242 is what X is going to be. And we get negative 111, which is B. Okay. The diagram above represents the melting of water, of solid water, which is ice, a 2 mole sample of ice at 0 degrees melted, producing liquid water at 0 degrees. Based on the diagram, which of the following best describes the amount of heat required for this process and the change that it took place at the molecular level? Okay, so I wish I could make this bigger. So we are given that number there. That number is actually kind of key. It's 6.02, we'll just call that 6 kilojoules per mole. So what that means is it's going to take 6 kilojoules per mole 6 kilojoules is released every time 1 mole of water freezes. Because that's what's happening here. Oh no, it's the other way around. When 1 mole of water melts, we're melting water. Fun fact, water is very unique because it's actually more dense as a liquid than it is as ice, which is why which is why icebergs float, which is why ice floats. So this is the ice, this is the water. I almost wrote H2O, water. So we need 6 kilojoules for every mole of ice we want to melt. So if we are melting 2 moles, that means we're going to need 12 kilojoules. It's not one of these two. And then 12 kilojoules of heat was absorbed to decrease the polarity of water molecules. 12 kilojoules of heat was absorbed to overcome some of the hydrogen bonding forces holding the water molecules in fixed positions in the crystalline structure. D is the right answer. It's still water molecules. We're not affecting the polarity of water molecules. It's still a water molecule here. It's still a water molecule here. What we are doing is we are breaking apart some of the hydrogen bonds, which is why it takes energy. Oh boy, this one looks like it has Hess's law. Based on the chemical equations and their associated enthalpy change shown above, which of the following identifies the quantities needed to calculate the enthalpy of formation, the standard enthalpy of formation for water in kilojoules per mole? Okay, so basically, how can we rearrange these 4 equations to get that equation? Maybe we don't even need to use all 4 of those equations. So let's start with water. Equation 4 has water. So I'm going to just jot down equation 4. We have H2O, H2O gas yields H2O water. We need to get this H2, and the only equation that has H2 is equation 1. It's in the product, so we need to flip equation 1. So we're going to get H2 yields 2H. Both are gas. And the enthalpy of that reaction, let me rewrite. So it's negative 44 for this one. This one's going to be positive 436 because we had to flip it. Next, let's look at this oxygen gas. For the oxygen gas, the only place oxygen gas appears is in reaction 2. It's in the products, it's on the wrong side, and we need to divide everything by 2. So we get 1/2 O2 yields O, and we get negative 249 divided by 2. I'm just realizing it doesn't actually have the numbers here, it just has the changes. So let me erase these. So this was enthalpy 4, this was negative enthalpy of 1, this was negative 1/2 enthalpy of 2. Do we make it? Does that get it? I don't think it does. I think we still have some things to cancel out, so let's use this equation 3. We need to cancel out, we still need to cancel out one of these H2O gases. We have one H2O gas in the product. So let's just write down equation 3. We have 2H plus O yields H2O gas, and that's just H3. Let's see what we got. H2O gas cancels. 2H cancels. O cancels, and we're left with H2 plus 1/2 O2 yields H2O. And our enthalpy is that. H4, or I guess it's going to go in order. Negative H1 plus negative 1/2 H2, so it's going to be this one, plus H3 plus H4. Okay, so the answer to 12 is B. A 2-mole sample of a compound undergoes the phase transition illustrated in the diagram above. This looks like condensation right here. It looks like we're going from gas to liquid or gas to solid. It could be deposition, but we'll go with condensation. The molar enthalpy of vaporization, so it is condensation, is 38.6 kilojoules per mole. Which of the following best identifies the change in enthalpy in the phase transition shown in the diagram? All right, we do have a 2 mole sample, and it's 38.6 kilojoules for every 1 mole, so it's going to be one of these 77.2 kilojoules, not 19.3. And the question is condensation exothermic or endothermic? Condensation is exothermic because we are forming bonds. We have no IMFs to IMFs. Condensation is also exothermic because gas is at a higher energy than liquid, so we have to release energy in order to go from gas to liquid. So it should be the one that's negative, which is D. All right, last question. Based on the reaction represented by the chemical equation shown above, what is the amount of heat released when 4 moles of H2S reacts with 9 moles of O2 gas? Okay, this one looks like a limiting reactant problem. We have 2 quantities of 2 different reactants, so we need to know what the limiting reactant is going to be first. Right away, I can see that the limiting reactant is going to be H2S. We can run through this reaction twice with 4 moles of H2S. We can run through this reaction 3 times, with 9 moles of O2. So H2S is going to run out first, but we can always just do the math to prove that as well. So let's set up some stoichiometry to get how much kilojoules of heat 4 moles of H2S will release. It's going to be this one. It's going to be C. If 2 moles releases that many, then 4 moles is going to release twice that many. But just for fun, let's run through how the stoichiometry would look. We have 4.0 moles of H2S. For every 2 moles of H2S, we get 1 mole of reaction. And for every 1 mole of reaction, we get negative 1120 kilojoules. So it's going to be 4 times this number divided by 2, which is negative 2240. All right, we have completed the multiple choice section. Still have the FRQ to go, at least for me. I don't know if you guys are watching this in or out of order. I'm just going to keep moving back and forth so it doesn't focus. And then we will end the video there, and I will see you guys in the next one. All right, that is it. Bye.